start. This is just, this was on the blackboard before. I just copied once more because we are going to use it. So we want to prove the following relations in this free group. So for any, I give myself two integers, L bigger or equal to m, bigger or equal to 1, and L is smaller than p times m. And then I consider in the mth filtration step of the free group, I consider all power series which are congruent 1 modulo p and degree L. Right? Remember, this meant that in degrees less than L, the coefficients are divisible by p. So, and then the assertion is this is contained, this is a product of an element in the p's powers of the mth filtration step times an element in the lth filtration step. So again, to be precise, I mean, here the product means just the element-wise. This is, product means products of an element in one factor and the element in the other factor, whereas p's power means the subgroup generated by the p's powers. This is maybe not an optimal notation, but I mean, I don't know a better one. So, I mean, the whole proof is kind of, I mean, because of the indexing, it's quite confusing. And I've tried various systems, and none is optimal. So we choose I mean, we have integers, right? I mean, the subportions of these filtrations are finally generated abelian groups. And we need to pick a basis for them and then representatives in the free group. So we have this sequence of integers starting from 0, then d1 is 2, and so on. So the successive differences are the ranks of these filtration steps. And elements, so which I denote by E, I start with 1, E1, E2, and so on in F, such that so the EI for I between dn minus 1 and dn. Actually, I don't need such that. This here, they lie in Fn and give a basis of Fn modulo Fn plus 1. So at first sight, this looks a little funny to enumerate it in this way, right? I mean, so up until dn, this is the basis for the next step, Fn modulo Fn plus 1. But if you do it in a different way, then somehow at other points it looks strange. So whatever you do, it's not optimal. Anyway, you see if, right, I mean, to check that this makes sense, I mean, take n equal 1, then this is d0, and this is d1, which is 2, so we have two possible indices, and f1, which is the whole group, modulo f2, which is the commutator group, has rank 2. So at least it's okay, this kind of indexing. So now we may write, so now let's take our element, we may write, so f is equal to so I'm only interested in it modulo the else filtration step. right? So which lies in the L is bigger or equal to M, so it lies in the mth filtration step. So there is some F1 with F1 in FL. And the rest I can now use these basis elements to write it down. And it starts, I mean, it lies in Fm. So it starts only with basis elements in Fm. So it starts with dm minus 1, dm minus 1 plus 1 to some power a dm minus 1 plus 1 and goes up to dl minus 1 a dl minus 1 f1, right? I mean the L step disappears, so I end with the L minus first step, and if this is L minus 1, then I have to go up to dl minus 1. Okay, and the claim is, that these exponents, they are all divisible by p. All a dm minus 1 plus 1 up to a dl minus 1 divisible by p, right? I mean, then they lie all in fm to the p, and so the product lies in there. Okay. So somehow we do this by induction. So assume has been shown already for the first, so for a dm minus 1 plus 1 up to some a dn with some n strictly less than L minus 1, but bigger than m minus 1, bigger or equal to m minus 1. So this includes the case, right? I mean, if this includes the beginning of the induction, if n is equal to m minus 1, then this is an empty, then this is an empty assumption. So now we apply to this first product, so this exercise over there, this was an exercise. All these things were exercises. So we take we take this here, we apply this here to the product of the first e's, so e e dm minus 1 plus 1 a d m minus 1 plus 1 up to e dn a dn. So all these exponents are, I mean, all these elements, right, they start with 1 plus, and the exponents, so I can apply this, exponents are divisible by p. So the whole thing is congruent 1 modulo p and degree p times m. I mean, in principle, I'm allowed to write here p times the order of the respective u, but this order is certainly, they are all bigger or equal to m, this order, so I can write m simultaneously here. Now, on the other hand, right? I mean, if I look at the remaining terms, so I claim that on the other hand, the f is congruent to this partial product here, em minus 1 plus 1 a. Modulo degree n plus 2. Because, I mean, the next ones, right, starts with dn plus 1. So, n plus 1, they are a basis of, I mean, everything which comes from here on lies in fn plus 2. Because, again, because of this indexing. So where is it? Right, it goes, the next ones start with dn plus 1, and so it's, I applied up there to n plus 1, it lies in, yeah, starts with dn. I'm confused, why is it, and it has to be, sorry. I put here, I have to put here n plus 1, right? I mean, actually, so it's important. I mean, I want to get for the step of the induction. So it's d sub n plus 1 up plus 1. So they all lie, the next ones, they all lie in fn plus 2, and therefore they disappear mod degree n plus 2. So now, right, I mean, now let's look at this. So f is congruent to the, I mean, I have to, I guess I have to repeat it. A, E, D, so L, wait a minute, no, I'm, okay, I want to compute here first, maybe I should write this down first, modulo P and degree n plus 2. So you see modulo P modulo P, I don't have to consider the first factors up to dn. And modulo degree n plus 2.
What is t here?
You really want to go from d sub m minus
Yeah.
1 to d sub
Actually,
maybe
you see, I want, look at this here first. I mean, modulo degree n plus 2, f looks like this here. But the first factors up to dn, this is this here, this disappears modulo p. So in other words, what remains here, modulo p and degree n plus 2, only are the factors e dn plus 1, a dn plus 1, up to e dn plus 1, a dn plus 1. And now this here is by the exercise part 1. I mean, this was exercise, maybe I write here 2. This is 2. Now I can only apply part 1 because I don't know yet anything about the exponents. Is 1 plus a dn plus 1 en plus 1, and now only the component in the respective degree, n plus 1. 1 plus a, sorry.
In this last step, do you want this thing congruent to 1 mod? This last line?
Yeah?
How do we know that it's congruent to 1? Degree n plus 2?
Just the assumption.
No, but that's p, mod p n.
No, but because the remaining factors in this here, the remaining factors, they all lie in.
Congruence is okay. Why is that congruent to 1?
Because the remaining factors are all congruent 1 modulo.
Don't we have p?
No, I'm looking at this here.
F is only 1 mod p time and big L. So sort of in between you show.
No, I have not yet used this assumption at all.
But it follows from what's written on the board. So you start with an F, which is congruent to 1 modulo with a certain degree and p. And suddenly in between in the proof you see that F is even congruent to 1 modulo degree or something.
This last line here.
Yeah, I don't think we need the congruent.
Yeah. No. I'm sorry, of course. Yeah. No. Sorry. Yeah, sure. I only want this congruence, of course. Sorry, so stupid. So here I think I'm also using right that I'm now using this. I think I'm also using these inequalities, Pm bigger or equal to L bigger or equal to N plus 2 at some point here, because to get this simultaneously for modulo degree N plus 2. And now, of course, this I can just, this is clear. This is the same as 1 plus dn plus 1 dn plus 1 plus adn plus 1 modulo. So now you see, I'm going to use the assumption on F. Again, note that L is bigger or equal to N plus 2. So this above there, the assumption holds modulo degree P comma degree N plus 2. And so so assumption on F implies that this expression here lies in P times the n plus first homogeneous component of the Magnus algebra.
Should these e's be e minus 1, or is that built into your notation? That when you have e dn plus 1 parentheses n plus 1.
I guess you're right. These should be okay. I should write them as, so I should write here somehow the 1 plus ei or so. I should write it this way from this. Yeah, that's right. They should be everywhere. They should be I mean, because if I use these congruences here, I have to, yeah, you're right. I mean, it only matters from this point on here, I think.
Maybe it is better to change that to e minus 1.
Yeah, I mean,
But a prime is.
I put a u, yeah.
So what is the definition?
So e something. Oh no! You see, no. You confused me. I mean, there's an upper subscript here, right? I mean, this is the component, the homogeneous component of the element e. I mean, this was okay. I mean,
No, that was part of the notation.
yeah. Okay, so this linear combination lies in p times of the homogeneous component of the Magnus algebra. But on the other hand, we know that this was the theorem 6.5. We know that these elements e n plus 1, n plus 1, up to e n plus 1, n plus 1 form a basis of L, the Lie algebra, intersected with m n plus 1, and that this was a direct factor, right? And the letter is a direct factor of m n plus 1. And so you see the coefficients must be divisible by p. Okay, and then we repeat this. And so inductively we get the claim. Okay, so this is somehow the general fact, and we apply this actually in only for two concrete elements. So first is 1 plus y to the minus p, 1 plus x to the minus p, and then 1 plus x times 1 plus y together to the p lies in f2 to the p times fp. And second, the commutator 1 plus x, 1 plus y to the minus p times the commutator of 1 plus x to the p and 1 plus y lies in f3 to the p times fp plus 1. And to be precise, this means, I mean, because here in this business we had also the additive commutator, this means the commutator in the free commutator. Okay, so we want to apply this maybe I do the first, and this is just explicit computation apart from from the proposition. So we want to apply this to this f, of course. So put f, this element, and then L is p and m is 2. And so certainly, right, I mean, 2p bigger or equal to p bigger or equal to 2, this is satisfied. So we have to show, to apply proposition has to show, so I mean, first of all, m is 2. I mean, m is 2, so I need that the element lies in Fm. So I need that f is congruent 1 mod degree 2. And then the other, I mean, L is p, so I also need that f is congruent 1 mod p comma degree of p. But somehow this is immediate from the, so for both, I mean, use exercise, and actually I think in the same sequence for this year you use the first part of the exercise, and for the other you use the other. I don't think I have to do this. I mean, you just start naively. I mean, you look at this element and apply the exercise, and then the result you multiply out, and you see what happens. And I mean, part 2 goes in exactly the same way. It's the computations are a little bit more, the explicit computations are a little bit more complicated, but it's again, it's straightforward from using these 2 exercises. Okay, so that's what we need from this general theory of the free groups in 2 generators. And now we apply this to get our final piece of structure on this graded Lie algebra. So, right, I mean, G was our group, G abstract group, and omega a p-valuation on it. And then we formed the graded group, and we know already is a Lie algebra over Fp. Graded Lie algebra over Fp. The Lie bracket is given by the commutator. But then also, of course, our axiom D was that right, it was that omega g to the p is omega g plus 1. So we want to use this. Somehow hasn't been used yet for the structure of this graded Lie algebra. And so now we prove the following. Now we use this corollary to prove the following. I mean, to prove 2 propositions. The first one, I think I will do only the proof of this one, is as follows. For any 2 elements, G in H and G, we have so omega of h to the minus p, g to the minus p times g h to the p is strictly bigger than the maximum of omega of g, omega of h plus 1. This is the important thing, but it's a easy consequence of it, which we'll need later on, is the following. Omega of g to the minus p to the n, h to the p to the n, is omega g minus h plus n. Right? I mean, it behaves, although of course it's not commutative, with respect to the omega, this behaves as I would be able to pull out the exponent of the product. Okay. Okay, so first of all, I can replace. I mean, we may assume that G is generated by G and H. Right? I mean, everything takes place inside this, all these expressions lie in this subgroup generated. If it's not the case, then I take this subgroup, restrict omega to it. Again, I have a p-valuation on the group. I mean, G is an abstract group here. There is no topological generation or anything. And so, then we have unique epimorphism, right, from the free group, from our free group onto G. 1 plus x goes to G, and 1 plus y goes to H. And then let's give this a name, psi. And then the first part of the corollary says that this expression we are interested in, g to the minus p, h minus p, sorry, I think it was the other way around, h to the minus p, g to the minus p, GHP, lies in psi f2 to the p times psi fp. Okay, so now we have to look what omega does on such a product. Now, psi of f2 is the commutator subgroup of G. So, as a normal subgroup, it is generated so it's generated by all the commutators, but then I can write, I mean, if the individual elements I can write as products of G and H and G inverse and H inverse, and then I can use those two identities to take them apart. So up to conjugation, I can reduce this to commutators for the factors in each component. So as a normal subgroup, it is generated just by these four G, H, G inverse, H, smallest normal subgroup which contains those. Yeah, maybe I don't need them, but you mean the other two? Yeah, that's right. I only need two of them, I guess. Yeah, that's right. But you see, by the axiom, so omega has values bigger or equal to omega g plus omega h on these commutators, which is strictly bigger because, I mean, these are both strictly positive, is strictly bigger than the maximum omega g omega h. So omega on the whole psi f2 has values strictly bigger than this, and then on the p's powers, so values of omega psi of f2 to the p are strictly bigger than maximum omega g omega h plus 1. So on this factor, it is okay what I want. Now the other factor, so similarly, psi of fp is a normal subgroup is generated by iterated commutators let me say with p entries from the set G inverse H inverse. So then omega value of omega is bigger or equal. So I mean the worst, I mean I do not know which of the two has smaller omega. So the, I mean I have, I mean if right, I mean it's of course what is completely uninteresting is if all p entries are either G inverse or H inverse. Forget about them. So only interesting are those where I have at least, where both somehow G and H occur. I don't know which one is the minimal one. But so the worst which can happen is that I have p minus 1 times the minimal one. So it's p minus 1 times omega times the minimum omega g and omega h. And I have 1 once the maximum. But now you see, now comes, so for the first time comes now the axiom A. So here, axiom A, right, says that this is strictly bigger than 1 over p minus 1. So this is strictly bigger than 1 plus the maximum. Okay, so here we use for the first time the axiom A. So part B is somehow an easy consequence. So by induction, suffices consider n equal to 1. And let's assume, right, I mean, by passing to the inverses, I mean, the order of g and h doesn't matter, so assume that omega g is the smaller one. And now apply E to the pair G and G minus 1H. And then we get that omega of so this is no h, right here, the old h. So I have g minus 1h to the minus p, then g to the minus p, and then the product of the two, which is simply h to the p, is bigger or equal to the maximum of omega of g and omega of g minus 1h plus 1. But by the axioms, this is the, I mean, this is here the bigger one. Right, I mean, by here, this is our assumption here. So this is omega g minus 1 plus 1, which is omega g minus 1h to the p. So you see these two elements have strictly different, I mean, they have different omega, and so their product, so it follows, the product of the two is just this here, omega g minus p h to the p. The product has to have omega, the smaller omega, which is this here, which is omega g minus 1h plus 1. Okay. So now let's apply this. Okay, so let u be any positive real number, and two elements in G such that, I mean, we are only interested now in the case that, let's say, omega of h is bigger or equal to omega of g, and u is omega of g. So then the proposition uh, 7.1e says that gh to the p times g nu plus 1 plus is equal to gp hp g u plus 1 plus. Right? I mean, if I bring this to the other side, I have exactly the expression there, and I mean, in principle, I get even something better, but I only need is strictly bigger than the maximum, so certainly strictly bigger than u plus 1. And so it lies in u plus 1 plus. So now if, moreover, if this, I have here strict inequality, right, then omega of HP is strictly bigger than u plus 1. So it lies in here. And so I have GHP G u plus 1 is equal to G to the P, G u plus 1 plus. So this means that the map going from, so which I call, yeah, okay, u G to u plus 1 G, sending G u plus to G to the P, G u plus 1 plus is well defined, right? I mean, the second equality here says it's well defined. If I take another representative here, quotient representative here disappears here. It's well defined. And the first thing says, I mean, right? I mean, in the grill, the addition is given by the multiplication, and to the P is compatible with it, so it's well defined and FP linear. So putting all those together, we have a graded homomorphism, graded at the moment FP linear map, which I call capital P. This is this operator in the title from grill G to grill G of degree 1. Now let me make, before we proceed, let me make right away. Okay, so in other words, I can view G is a graded module over the polynomial ring Fp in the variable P, capital P. And let me make right away the remark that this module G as an Fp capital P module is torsion free. Right, so let's assume, so Q of P a non-zero polynomial, say with highest term I mean, this is a standard argument, a p to the d, and say xi some xi u non-zero element, I mean non-zero element in G such that Q of P applied to xi is 0. Let's say maybe u0, here u0 is the highest term, yeah? Xi u0 highest term. Then, of course, because P has degree 1, P has degree 1, it follows that already a P of xi u0 has to be 0. Because, right, I mean, the smaller ones, the whole thing is graded. The smaller ones cannot catch up in the degree. They have we'll have smaller terms in the polynomial applied to smaller terms in psi will end up in degree strictly less than u0. But I mean, axiom D implies, right? I mean that I mean, we know a little bit more. We know that the p-valuation of g of the p's power goes up exactly 1. So if this was non-zero, this is non-zero. So the operator pi is injective.
So, AP to the D.
AP to the D, yes, thank you. So the operator pi is injective, and this is a contradiction. Okay, so this is important for later. But now let's first see the last piece, which maybe I will not. I mean, now we are using here the corollary 2i. So this is proposition 7.3, which says that omega g commutator gh to the minus p times commutator of g to the p times h is strictly bigger than omega g plus omega h plus 1. And maybe I don't do this. I mean, this is, the proof is exactly the same as the one of 7.1, based now on the second part of this corollary. So it follows from corollary 6.7 2i. In the same way as the previous proposition, followed from the first part. But so this means, so this implies that we have the commutator of g to the p and h modulo omega g plus omega h plus 1 plus is the same, right? We have strict inequality here. So we can compute modulo this expression plus r, and then it becomes equal to the coset of this element, g h p g. So the commutator here in the group becomes in the graded group the Lie bracket, and the p's power becomes the operator p. So we see that the Lie bracket in group G is FPP bilinear. Right, I have to do this only in one component because of the antisymmetry. So, okay, so now we have everything together. The G is a graded Lie algebra over this polynomial ring. So this is really somehow the discovery of Lazare. I mean, one of his fundamental discoveries, that you have this associated with this p-valuation, you have associated this fundamental object. Okay, so now we can, now let me, I think now we don't need this anymore. Okay, so now I can come to the definition of the Okay, so from now on, G is from now on, G is a profinite group. Right, so far it was an abstract group, but now from now on we are interested only in profinite groups. Omega is and omega is a p-valuation on G, which I assume to define the topology, which for the moment, which defines the topology. These are our assumptions, right? And then, of course, these quotient groups G by, the G nu are then open subgroups, so they are all finite. Then is finite, and G is the projective limit of these finite groups. And actually, of course, the axiom D implies that this is because by raising to pth power over and over again, I can make the omega value arbitrarily large. So I see that these are all is a p group. So it follows that G is necessarily pro p. Okay, and now we make the following definition. Right, we do know, the mark has disappeared, but we do know, we have this object, and we do know by this remark, in addition, that it's a torsion-free module over this polynomial ring. So the pair, for the moment, the pair T, omega is called of finite rank if gril G is finitely generated as a FP capital P module. Right, and so I will now okay, and then of course G is even a free FP module, finally generated torsion free over this principal ideal domain is free, and so I can define the rank of G, omega is defined to be the rank of this module. It's called the rank. So, these are provisional notations in some sense.
The freeness is not obvious.
Sorry?
The freeness is not obvious.
The Freeness is obvious.
Oh, there's
yeah.
no torsion. You
There's
mean
no
it's
torsion.
finitely generated, yeah,
Yeah.
of course.
Elementary divisor theorem. So these notations are provisional insofar. We will later see that they do not depend, neither the property being of finite rank nor then the actual rank does depend on the choice of omega. As long as one such omega is present, yeah, as long as you have one such omega, all the other possible ones, but I mean this we cannot see right now. This will come at quite a bit at a later stage, and so I use until then I use this precise notation. Maybe let me quickly mention this lemma and finish with it. So if g, omega is of finite rank, then the set of values of omega is discrete in the discrete subset of the real line. And so for this, look at decompose. There is an obvious whenever, for every such created thing, there is an obvious decomposition according to the real numbers between 0 and 1. G nu, where G. Sorry. Here I read. So now this is defined to be the sum of all homogeneous components. I take the nu plus an integer. Right? I mean, certainly, this is a trivial decomposition as an abelian group. I mean, any degree certainly is something between 0 and 1 plus an integer. But the point is, because our operator is of degree 1, is a FP P invariant decomposition. And so, because the thing is finally generated, only finally many such summands can occur. And then, of course, there is some initial one. I mean, of course, this can be the first ones, for nu, I mean, right, this can be 0. But somewhere, from a certain point on, there is a first nu which is non-zero. And then that's the first occurring value. And then all the other values are this one plus an integer. So you see what I get is, so the values follows the values is the monoid generated by finally many positive numbers. And that's a discrete subset. I mean, maybe I should say the values lie in the. Maybe I should say, is it maybe to be cautious? Is contained. I think I should say is contained. In where these finally many numbers are the minimal occurring, the minimal in each of these, I have only finally many, and in each of these it's the minimal one of those which actually occurs, where the grid is 0, is non-zero. Okay, I finished with that. It's much simpler. You will see later on how to compute the rank. It's purely group theoretic. There's an easy group theoretic formula for it. You don't
And
need
finite
more.
rank is not equivalent to finitely topological generated.
We will all, not quite, we will all discuss this. Be patient. Next time, we will discuss this relation we will discuss next time. The thing with the rank needs a little bit longer.
Yeah, which Profi groups have omega variations, evaluations?
Yeah, sure, we will all this will be discussed.
Lots of secrets.
I mean, it's not possible to have this course